Welcome to our Lagari ZD01 UAS Flight Readiness Review. This video will give you a brief overview of our team and UAS. We are 9 students from Yıldız Technical University Mechatronics Engineering Department. Now we will introduce this year's team members. Experience, roles and responsibilities. Tolgahan Akbulut, undergraduate senior team captain. Flight line role, team coordination and liaison with the judges. Mehmet Öztekin, safety pilot. Abdurrahim Ayaz, undergraduate sophomore, interoperability, development and image processing sub-team. Flight line role, primary image processing station operator. Onur Sevi, undergraduate sophomore, obstacle avoidance and target detection. Flight line role, backup image processing station operator. Berk Kaynak, undergraduate senior, mechanical and aerodynamics sub-team lead. Flight line role, aircraft installation and director. İsmetcan Hasan Çebi, undergraduate sophomore, mechanical sub-team and airdrop system. Flight line role, aircraft installation. Faruk Okumuş, undergraduate junior, electronics and communications sub-team lead. Flight line role, communications systems controller. Müçteba Uzunoğlu, undergraduate junior, flight line control simulation. Flight line role, safety inspector. Mert Çelikol, undergraduate junior, flight control and navigation systems sub-team. Flight line role, backup GCS operator. Yunus As, undergraduate senior, autonomous flight and control sub-team lead. Flight line role, primary GCS operator. System overview. Lagari designed and developed ZD01 to accomplish all of SUAS competition tasks while paying attention to the rules. Last year, components didn't have a specific place, so there was a complicated system in the fuselage. This year, we designed new avionic boxes in order to reduce system faults and increase safety. The team spent their time to fly autonomously, manufacture a new fuselage, develop algorithms for image processing and obstacle avoidance. Last year, the fuselage caused more drag and it had empty volume. We also had some problems with the wings of the UAV. The dihedral angle made it difficult to manufacture wings. This year, ZD01's fuselage was designed according to the components that will be used. So this provided the great advantage in terms of friction and fuselage layout. The wing area was increased to reduce the cruise speed. Thus, the aircraft can fly slower and capture more images from search area during the mission. The wings were supported by carbon fiber pipes as spars, extending into the fuselage to increase the strength and durability. For easy transportability, the system was designed to be detachable in a short time. To resolve the disorder in the fuselage, 2 avionic boxes were designed. The payload box contains the necessary parts for the ODCL mission. Firstly, our Sony FSB camera takes the photo and sends it to the Odroid XU4. Odroid saves the data. Jetson TK1 downloads the data from the Odroid and processes the images. Switch connects all components that uses the network in the UAS. M5 Bullet is used for wireless network communication with the ground station via 5.8 GHz Wi-Fi link. The control box includes the essential components to fly manually and autonomously. Pixhawk 2.1 Cube is responsible for autonomous flight. It's connected with radio receiver that provides the communication between the UAV and the safety pilot. RFD 900 Plus supplies long-range telemetry communication in autonomous flight. Planned tasks and expected performance. Autonomous takeoff, attempted, high confidence. Autonomous flight, attempted, high confidence. Waypoint capture, attempted, high confidence. Autonomous landing, attempted, low confidence. Stationary obstacle avoidance, attempted, high confidence. Moving obstacle avoidance, attempted, low confidence. Search area, attempted, high confidence. Off-axis, attempted, low confidence. Autonomy, attempted, medium confidence. Geolocation, attempted, high confidence. Air delivery, attempted, high confidence. Interoperability, attempted, high confidence. Developmental testing. Wing loading test. A wing loading test was conducted to simulate the flight circumstances. According to Vortex lattice method, the load was distributed on the wings of a maximum load of 2g. We measured the difference of unloaded and loaded wings, then we concluded that the wings will perform sufficiently for the maneuvers. Main landing gear test. Stress analysis was conducted in ANSYS platform for our main landing gear. According to the results, the proper structure was selected. After the manufacturing, we also performed a real-life test on the landing gear and compared it with the analysis. It was concluded that the landing gear can resist up to 3g force, which is equivalent to 276.6 newtons. Thrust test. Last year, we had difficulties with our propulsion system. 6.5 kilograms of thrust was required to operate the plane steadily. This year, several tests were conducted with different motors, and it was concluded that the propulsion system was sufficient for our thrust-to-weight ratio. Flight simulation. To improve the system specifications, we simulated our flight controller by using hardware-in-the-loop. Hardware-in-the-loop is a type of real-time simulation which provides as if it flies in real time without using aircraft. Pixhawk and MATLAB communicated with each other by using UDP protocol. To visualize the overall system, X-Plane was used as a flight simulator. Autonomous takeoff. Before the flight, the UAV must be programmed with the mission, including the takeoff. The first waypoint is the home position, where the plane starts the takeoff. There are two parameters to execute the takeoff command: the minimum pitch and the takeoff altitude. To stabilize tracking on the runway during takeoff, ground steering was tuned in advance. After 10 attempted autonomous takeoffs, 9 of them were successful. Autonomous flight. In autonomous flight, we tuned the aircraft PID and total energy control system based on parameters. PID controller was so effective, therefore we executed several flight tests to tune PID parameters for the aircraft. The speed and height control of the UAV was improved by tuning total energy control system. Out of 20 minutes of flight, only 5 minutes were on manual mode on each test flight. Autonomous landing. To perform autonomous landing, more experience and knowledge are required. In order to achieve this, we analyzed the behavior of the UAV during manual flights by using log data. To observe more accurate altitude data, we use laser altitude sensors whose range is 40 meters. It measures the altitude of the vehicle precisely. After that, we determine some optimal value of some parameters such as flare point and airspeed. Our team was successful at 2 out of 5 auto landings. Waypoint accuracy. Waypoint navigation requires accurate position information, so we used extended Kalman filter to improve the GPS data. Additionally, L1 controller was used to provide control path. It allows the aircraft to smoothly transition between waypoints. Also, sensor fusion improves navigation performance. Obstacle avoidance performance. Lagari team used an algorithm based on rapidly exploring random tree. This algorithm optimized the escape path and added 30 feet offset points for safe maneuvers. 3 test flights were conducted with 18 moving and stationary obstacles. Throughout these tests, 10 stationary and 2 moving obstacles were avoided. Imaging performance. This year, images taken by UAV's camera were sent to image console at the speed of 1 frame per second to ensure full coverage of the field. Furthermore, our camera's 10x zoom feature helped us process objects with more adequate images. To increase the number of images taken, we decreased the shutter speed and increased the aperture of our camera. From the leading improvements, we needed 40 by 40 pixels for image detection, classification, and localization from 300 feet. Detection and classification performance. We have done autonomous and manual detection. The manual detection was done by imaging console. Convolutional neural network method was used to obtain trained data from test flights. During these tests, frames were obtained within 8 hours. 12% of these images had objects. Localization performance. Lagari team wrote an algorithm to calculate the location of the detected objects from the information of its place by taking the image and geolocation of ZD01. At last, Localization data was combined with other image information and sent to judges. Throughout testing, 26 objects were found with 10 meters average error from object's original position. Air delivery performance. Air delivery system was tested atop a building which has a length of 50 meters for 5 times and for 10 times from the plane. The payload survived and remained intact in each of these drops. On average, the payload landed 12 meters away from the spot. Mission testing. Lagari team is confident in the capability of the ZD-01 system to complete predefined competition tasks. 10 full mission test flights have been performed while analyzing different mission purposes. Lagari team performed full mission tests elaborately and applied common and specific checklists in subsystems for every flight. Lagari team prepared backup subsystems for every single system in a case of failure. After evaluation of checklists, if any systems did not meet competition requirements, backup subsystems were integrated into the primary system. Navigation and target geolocalization systems were tested simultaneously to ensure the system was reliable and ready for the missions. Capturing image development system was tested along geolocalization to ensure the captured image's accuracy and consistency. Obstacle avoidance system was tested in both simulation and real flight. Success rates were alike in both cases. Obstacle avoidance tests were conducted autonomously to produce safer, accurate, and optimal paths. In mission tests, air delivery was tested in the plane and on the ground repeatedly. Payload was reliable, and it remained intact in 100% of the drops within 12 meters of the target. Those tests ensured that Lagari team is ready for the real competition and the whole process is flawless during flight operations. We are very excited for Maryland and awaiting a full-on competition.